space. It's infinitely big, and there are an infinite number of things in it. But there are not an infinite number of different kinds of things. So this is my attempt to try and collect all of the different kinds of things in space in one video. Looking up from our Earth into the sky, we see our solar system. At the centre is our Sun, a yellow dwarf star that's lived for about 4.6 billion years and will live for 5 billion more before burning out. Around the Sun orbit the terrestrial planets, which are made mostly of silicate rocks or metals, and the gaseous planets, which are split into the gas giants, which are mostly made of hydrogen and helium, and the ice giants, which are made of heavier elements like oxygen, carbon, nitrogen and sulfur. In between Mars and Jupiter, we've got an asteroid belt, which is the relic of the stuff of the early solar system, which we think never formed a planet due to the strong gravitational effect of Jupiter. There are other asteroids in the solar system, some of which become meteoroids when they hit the Earth's atmosphere. And we get comets, which have highly elliptical orbits around the Sun and were caused by the outward motion of Neptune 4.5 billion years ago. We also have dwarf planets which haven't managed to clear their orbits of other objects, like Ceres in the asteroid belt and Pluto and others in the Kuiper belt, which is a region beyond Neptune similar to the asteroid belt, but far wider, containing many small bodies made of rock and metal. And of course, we have moons, like our moon and the moons around other planets. Beyond the Kuiper belt, we have the Oort cloud, a theoretical cloud of icy objects surrounding the Sun in all directions. And finally, we have the heliosphere, a large bubble around the solar system created by particles coming from the Sun, called the solar wind, hitting particles from the rest of the galaxy, the interstellar medium. And of course we mustn't forget cosmic dust, microscopic collections of matter scattered throughout the universe. Looking beyond our solar system, we get to our galaxy, the Milky Way, made of about 400 billion other stars spinning in a giant spiral. The solar system takes about 250 million years to orbit the Milky Way, and it's done this about 20 times in the lifetime of our Sun. In the centre of the Milky Way is a supermassive black hole with a mass 4.6 million times that of the Sun. We think there's probably a supermassive black hole at the centre of every galaxy, and they can have masses of up to 1 billion times that of our Sun. When we look up into the night sky, most of what we see are stars. And there are many different kinds of stars in the galaxy. 95% of stars are main sequence stars, which break down into red dwarf, orange dwarf and yellow dwarf stars. Red dwarf stars are the smallest, much smaller than the radius of the Sun, but the longest lived, estimated to live for thousands of billions of years due to their slow burn. Orange dwarf stars are a bit smaller than the Sun and will live for tens of billions of years. And yellow dwarfs, like our Sun, live for about 4 to 17 billion years before expanding into red giant stars. Smaller than red dwarfs are brown dwarfs, which aren't really stars because they were never massive enough to create fusion in their cores. They're about the same size as Jupiter but have at least 13 times the mass. The brightness of many stars varies over time, and these are known as variable stars. There are a few different kinds. Intrinsic variable stars, their luminosity actually changes due to a change in size, whereas with extrinsic variables, the brightness changes because of an orbiting companion moving in front of it, like a binary star system or extrasolar planets. And some giant or supergiant stars have irregular changes in luminosity. Cepheid variable stars are very valuable to us because they've got large variations in both size and temperature with a very stable frequency. Because of this strong relationship between luminosity and the frequency they pulsate, they're used to determine accurate distances in the universe. They're known as standard candles. Much bigger than the main sequence stars are the blue giants with a radius of 1.4 to 250 times the radius of the Sun, and much shorter lives, existing for 3 to 4,000 million years. At the end of their lives, they can cool into red giants, supergiants, or hypergiant stars. Red giant stars have a radius of 20 to 100 times the radius of the Sun and burn for a few 100 million to 2 billion years before exploding to make a planetary nebula, with their cores shrinking into a white dwarf star. A white dwarf star is also the final destination for orange and red dwarf stars. White dwarf stars make up 4% of the stars in the galaxy and are tiny and dense, roughly the mass of the Sun squeezed into the size of the Earth. And they're dead, no fusion is going on in their cores, and they only glow due to their residual heat energy. They will live for trillions and trillions of years, growing dimmer and dimmer until they end up as black dwarfs, which don't yet exist because the universe hasn't been alive for long enough. White dwarfs will be the final state for more than 97% of the stars in the universe. For the truly massive stars, a different cosmic journey awaits. The red super and hypergiants have much shorter lives of only 3 million to 100 million years. These colossal stars with radiuses 100 to 2,000 times that of the Sun end their lives in a humongous explosion known as a supernova, where they throw off their outer layers into a nebula known as a supernova remnant, while the core collapses into either a neutron star or a black hole. Stars larger than 40 times the mass of the Sun are likely to collapse into a black hole, an object so dense and massive that not even light can escape its gravity. This makes them completely dark, and at their centers a gravitational singularity rips a hole in the fabric of space-time. They are the most extreme and fascinating objects in our universe. For stars that are not massive enough to form a black hole, they collapse into a neutron star, where the combined gravity of the insane mass of the star overcomes the ability of electrons to keep atoms separate. The atoms collapse, the electrons and protons combine into more neutrons, and it forms an incredibly dense ball of neutrons like a giant atomic nucleus. They have a mass of about 1.4 times the mass of the Sun, but squeezed into a radius of only 5 to 15 kilometers. This is so incredibly dense, a sugar cube-sized piece of neutron star would weigh as much as Mount Everest. Neutron stars are normally left spinning very quickly, and they've got incredibly strong magnetic fields, millions of times stronger than anything we've ever created on Earth. This magnetic field spews out electromagnetic radiation at the poles, and as they spin around, it sweeps a beam across the universe, making a precise pulse when it passes. These are called pulsars, and some of them revolve incredibly quickly, several hundred times a second, which is just mad. The neutron stars with the strongest magnetic fields are known as magnetars, and they could be the explanation for mysterious signals we see in the sky like soft gamma repeaters and anomalous X-ray pulsars. An X-ray pulsar is a binary system where a normal star and a neutron star are orbiting around each other. The neutron star sucks matter from the main star, creating high-energy beams of X-rays at the poles. I've covered the death of stars, but what about their births? Stars form from the gas and dust of the stars that exploded in the distant past. Clouds we call nebulae. A protoplanetary nebula is the final stages of the formation of a solar system, the star and planets forming out of the gas and dust. There are many other kinds of nebula too. An H2 region is a cloud of ionized hydrogen gas where star formation is taking place. An emission nebula is where a nearby hot star ionizes its gas and then it emits light at different frequencies. However, if the light from the star is not energetic enough to ionize the gas, instead it'll scatter off it, making a reflection nebula. And some nebulae are so dense they block light coming through. These are called dark nebulae. And the final feature of our galaxy are star clusters, which come in two categories. Globular clusters are tight groups of hundreds to millions of stars which are gravitationally bound, while open clusters are a few hundred stars that are more loosely spread out and are not gravitationally bound. Until about 100 years ago, we thought that the Milky Way contained all of the stars in the universe, until Edwin Hubble showed that the Milky Way was just one galaxy of many. And now we know that there are 1 to 2 trillion galaxies in the observable universe. The Milky Way galaxy is a spiral galaxy, but other galaxies broadly break down into elliptical, spiral, and barred spiral galaxies. Shell galaxies are elliptical galaxies which are made from concentric shells of stars. Lenticular galaxies fall somewhere in between elliptical and spiral galaxies. Occasionally, galaxies collide and interact, and because of this, some galaxies don't fit these broad categories. For example, ring galaxies have an empty core and a ring-like collection of stars around it, which may have been caused by a smaller galaxy moving through the middle of the larger one. And irregular galaxies are those that have a strange shape due to some interaction in the past. There are superluminous galaxies, 4 times bigger than the Milky Way, but most galaxies in the universe are a lot smaller than ours, and they're called dwarf galaxies, containing a few billion stars about 100th the size of the Milky Way, and often they orbit the larger galaxies. Some galaxies have very active galactic cores where material falls into the central supermassive black hole, creating jets of particles travelling close to the speed of light. These are called blazars if the jets are pointing directly at us, but radio galaxies if the jet is pointing away, as all we see are the radio waves being emitted by the jets. Quasars are the most distant and most energetic of the active galaxies, their central cores emitting up to 100 times the luminosity of the entire Milky Way. Now we get to the mysterious things in the universe. Things we see but don't understand. Gamma ray bursts are insanely energetic bursts of electromagnetic radiation from distant galaxies, and the brightest events that occur in the universe. We think that they come from massive stars exploding in a supernova or from mergers of neutron stars. Fast radio bursts are mysterious short pulses of radio waves caused by some high-energy process, generating as much energy in a millisecond as the sun does in 80 years. Some of these fast radio bursts are repeating, coming from the same source over and over again, and we have no idea what is causing them. Dark matter is a mysterious form of matter that gives galaxies extra mass. Without it, they would fly apart. Even though it makes up approximately 85% of the matter in the universe, we don't know what this dark matter is, because it doesn't interact with our ordinary matter. Our best guess is that it's some form of undiscovered subatomic particle flying around in space, but we've got no evidence for this yet. The solar system and galaxies are held together with gravity, because gravity pulls things together. But when we look at galaxies in the distant universe, we see that they're accelerating away from us. This is really weird because it means that there's a mysterious force throughout the galaxy that's pushing everything apart at an accelerating rate, like a kind of anti-gravity. We call it dark energy, and it makes up 68% of the energy in the universe. Even though we've given it a name, we've got no idea what it is. As we go to the largest scales in the universe, we see galaxy clusters, then superclusters, and the dark voids between them. Then we get to the cosmic microwave background, the signal from when the universe first became transparent 380,000 years after the Big Bang. Behind this, we can't see anything with light, but we will be able to peer behind it with gravitational wave astronomy, right back to the Big Bang, which is as far as we'll ever be able to see in the universe. This makes it the edge of the observable universe at 46 billion light years away. We know that there's still stuff further away from us than that, but we'll never see it because it's travelling away from us faster than the speed of light. And I said at the beginning the universe is infinite, but we don't actually know whether the universe is infinite or finite. That's another mystery to be solved. So that's the universe all in one go. At least most of it. I did have to drop a few things for the sake of time. Let me know in the comments if you think I've missed anything important. And one thing that is finite is this poster, which you can get your hands on. Links in the description below. And I've heard from some of my subscribers that they're not seeing my latest videos pop up on their feed. This is a thing that happens sometimes on YouTube, and the solution is to press the notification bell next to the subscribe button. So if this is happening to you, that's what to do. Also, big thanks to my Patreon supporters. Your support means I can justify spending the time that it takes to make this high quality science content. And if you'd like to join the gang, check out my Patreon page here. Alright, thanks for watching, and I'll see you on the next video.